Chapter 6, Section 3, Solving Systems or Linear Systems Using Matrices. The previous two sections had us solving systems using either substitution or elimination, which were great. I hope to show you how using matrices can be very efficient and a very organized way of solving a system. Let's start with the definition. A matrix is a rectangular array of numbers arranged in rows and columns written within a set of brackets. Let me show you a system and how we can rewrite the system or represent the system of equations using a matrix. Check this out. Solve the following system using matrices. So we have 3x minus 5y is 7 and x plus 2y is equal to 6. So when I rewrite this using a matrix, first of all, I need my brackets, and the first row in my matrix will correspond to the first equation within my system. And when I write down my first row, I'm only writing down the coefficients of the first equation. The coefficients are 3, -5, and +7. Those are my entries for the first row. Okay? And when it comes to the second row, the entries in my second row correspond to the coefficients of my second equation, namely 1, 2, and 6. So this is the matrix that corresponds to this system of equations. Okay? And of course, you can go the other direction as well. If I give you a matrix like this, 3 represents the coefficient of x, -5 represents the coefficient of y, and 7 is your constant term. The same thing for the second row. So you can read this as 3x minus 5y is equal to 7. Down here, 1x plus 2y is equal to 6. Our goal is to solve this system, that is to find the point of intersection of the two lines using matrices. Now, our goal is to rewrite this matrix in a special form called reduced row echelon form. Let me show you what reduced row echelon form is. So here it is. Our goal is to transform this matrix here to be in something called reduced row echelon form. This is reduced row echelon form. Notice that you have 1 as the first entry in the first row, followed by a 0. And here, the third entry, which is your constant here, just represents any number, any real number. The second row starts with a 0 and then a 1 in the second row, second column entry, followed by any number. Okay, so I always tell my students that reduced row echelon form has 1s along something called the main diagonal. So 1s here and then 0s here in the opposing entries. This here ordered pair will end up being the point of intersection. That is to say, this number, comma, this one will end up being your solution. Okay, now, how do I get my matrix to go from looking like this to reduce row echelon form? Well, the 3 things you're able to do, the 3 manipulations you're able to make on your matrix are called elementary row operations. Okay, let me tell you what these 3 operations are. They're basically the same 3 operations that you were using with the elimination method and the substitution method, but they're just now represented as row operations, but they're the same things that we've been doing. Here they are. So first, any 2 rows can be swapped. You're allowed to swap any of the rows. Any row can be multiplied or divided by a non-zero constant. So like you can multiply an entire row by 2, or you can divide an entire row by -3 or whatever, as long as it's not 0. We can add a multiple of one row to another row. We'll be using that operation often. So these are the 3 things that you're able to do to your matrix in order to get it in reduced row echelon form. All right, so here we go. I'm going to now start with my matrix here, and I'm going to start performing some operations on it in order to get it to look like reduced row echelon form. You want to take a really good screenshot of this reduced row echelon form. You want to remember what it is you're trying to achieve. A 1 in the first row, first column entry, a 1 in the second row, second column entry, and then zeros above and beneath those leading ones. Okay, so let's go for it. The process that I'm about to show you now actually has a special name. It's called the Gauss-Jordan Elimination method of us rewriting a matrix in reduced row echelon form, named after two amazing mathematicians. One is named Gauss and the other one is Jordan, and so this process is due to their work. Here we go. Here's our matrix. We want to get this in reduced row echelon form. What that means is I need a 1, a positive 1, in this first row, first column entry. I can achieve that if I just swap the two rows. If I swap this entire row with this other row, this 1 up down here will end up being up here. All right? So I'm going to be very careful to write down what it is I'm doing. All right? Now this is very important. In order for you to get any credit at all with this kind of work, you have to write down what it is you're doing. So this is how I'm saying row 1. Oh, sorry. This is my notation for saying that row 1 will be swapped with row 2. Okay, very good. When you swap the rows, now you have a leading 1 is what we call it. The first row, first column entry is a 1. Very good. All right, now we're going to shift our attention to this entry, the second row, first column entry, which is a 3. We need it to be a 0. Okay, now what I'm going to do is I'm going to use the row operation number 3. I'm going to add a multiple of the first row to the second row. And this is what I'm going to do. I'm going to take row number 1 and I'm going to multiply it by -3 and add it to row 2. I'm going to say that again before I write it down. I'm going to take row number 1 and I'm going to multiply it by -3 and add it to row 2. If I do that, 1 times -3 will be -3, and then when I add -3 to 3, I get 0. Okay, that's how I'm going to get that 0. But all the while, I do not want to change row 1. Okay, it is row number 2 that I'm changing. Okay guys, I wrote down what I'm doing. I'm multiplying row 1 by -3 and then adding it to row 2, and that will be my brand new row number 2. Okay, it's row 2 that's changing. What I tend to do is I write down row number 1 first so that I don't accidentally change it. I'm not changing row 1, I'm changing row 2. And I'm changing row 2 by doing this. All right, so here we go. See if you can follow me here. I'm going to multiply every entry in row number 1 by -3 and then add it to its corresponding entry in row 2. So follow me here. 1 times -3 is -3, and -3 plus 3 is 0. Let's do that again. 2 times -3 is -6, and -6 plus -5 is -11. Let's do it once more. 6 times -3 is -18, and -18 plus 7 is -11. Okay, so that's what we have. Now, so that was row operation number 3, adding a multiple of one row to another. We have the leading 1 in row 1, first row, first column entry. We have the 0 in the second row, first column entry. Now I need this entry to be a positive 1. I can achieve that by dividing this second row by -11. If I multiply this entry by itself, it becomes positive 1. Okay, as usual, I'm going to write down what I'm doing. I'm changing row 2 by dividing it by -11, and this will be my brand new row 2. Now, what row am I changing? I'm changing row 2. Which row am I not changing? I'm not changing row 1. So let me copy down row 1 here before I do anything else, just to make sure I don't accidentally change it. Now here we go. 0 divided by negative 11 is 0. Negative 11 divided by negative 11 is 1. That's what we wanted. And then negative 11 divided by negative 11 is 1. Okay? Now, all we need to do next, all that's remaining is this entry here. The first row, second column entry needs to be a 0. We can get that to be a 0 if we multiply the second row by negative 2 and adding it to row 1. But when I do that, I don't want to change row number 2. I want to change row number 1. Okay, as usual, I wrote down what it is we're going to do. We're going to take every entry in row 2, multiply it by negative 2, and then add it to its corresponding entry in row number 1. Okay, and this will be my brand new row 1. I'm not changing row 2, so I copy down row 2 before I accidentally change it. Now here we go. I'm going to take every entry in row 2, multiply by negative 2. 0 times negative 2 is 0, and 0 plus 1 is 1. So I don't lose my leading one that I worked, sort of hard to get. Let's keep going. 1 times negative 2 is negative 2, and negative 2 plus 2 is 0. That's what you and I were after. 1 times negative 2 is negative 2, and negative 2 plus 6 is 4. So we did it. This is reduced row echelon form. You got 1s along the main diagonal and 0 above and beneath your leading ones, and this is your solution. Okay? So what I want you to do is, can you now rewrite this system, rewrite the matrix back in system form? So remember that the first row corresponds to the coefficients of the first equation. So therefore it's 1x plus 0y is equal to 4. Let's write that down. 1x plus 0y is equal to 4. The second equation says 0x plus 1y is equal to 1. So I hope you can see that this basically means, right? This basically means the first equation just means that x is 4, and the second one says y is 1. So our ordered pair is 4, 1. This is the final answer. This is the point of intersection between the two equations, right? Between the two lines, the point at which they intersect. A little bit of vocabulary work for you. Because there is a solution, the system is called consistent. All right, so it's a consistent system. If there's no solution, then the system is said to be inconsistent, and we'll definitely look at an example like that pretty soon. All right, we did it, guys. All right, here's our brand new system. Let's write the corresponding matrix. Okay, sometimes people call this the augmented matrix. All right, so the first row will be 7, negative 4, 18. And then the second row will be 2, 3, and 1. Make sure you're using brackets. All right, cool. What we want to do is write this matrix in reduced row echelon form. Okay, so we need this first entry to be a 1. What I can do here is I can multiply the second row by negative 3. That will give me negative 6. And if I add that to 7, that will give me 1. Now, this will change row number 1. I do not want to change row 2 at the moment. I'm only trying to change row number 1. Okay, guys, this is what we're doing. We're going to multiply row 2 by negative 3 and then add it to row 1, and that'll be my new row number 1. I rewrote row 2 right now so that I don't accidentally change it. Now here we go. 2 times negative 3 is negative 6, and negative 6 plus 7 is 1. That's what we wanted. Keep going. 3 times negative 3 is negative 9. Negative 9 plus negative 4 is negative 13. 1 times negative 3 is negative 3. Negative 3 plus 18 is 15. Cool? So I'm hoping you're seeing that this is very efficient because it's very organized, right? You're not writing down variables, you're just writing down numbers in a very organized way. Okay, we got our leading one. What we want next maybe is this entry here to be a 0. We can get this to be a 0 if we multiply the first row by negative 2 and add it to row 2. I don't want to change row 1 at the moment. I'm trying to change row 2. I'm going to multiply the first row by negative 2 and add it to row 2. All right, so here we go. Row number 1 being multiplied by negative 2, add it to row 2, that's my brand new row 2. So here we go. 1 times negative 2 is negative 2, plus 2 is 0. That's what you and I wanted. Negative 13 times negative 2 is positive 26, plus 3 is 29. Finally, 15 times negative 2 is negative 30. Negative 30 plus 1 is negative 29. All right, we did it. We have a leading 1 here, a 0 underneath it. Now I need this second row, second column entry to be a positive 1, and I can achieve that if I divide row 2 by 29. Okay, I wrote down what it is we're doing, row 2 divided by 29, and that's my brand new row number 2. I'm not changing row 1, so I copied it down first things first. All right, here we go. Row 2 divided by 29. 0 divided by 29 is 0. 29 divided by itself is 1. Negative 29 divided by 29 is negative 1. All right, cool. I hope you can see right now, if you pause and just observe what you have 0x plus 1y is negative 1. That is to say, y is negative 1. You already have your y value of negative 1. All we need now is x. So let's keep going. We need this negative 13 to be a 0. We can get it to be a 0 if we multiply row 2 by 13 and then add it to row 1. So here we go. We're going to multiply the second row by 13 and add it to row 1, and that'll be my brand new row 1. All right? So 0 times 13 is 0. 0 plus 1 is 1. So we're not losing that leading 1 there. That's good. 1 times 13 is 13. 13 plus negative 13 is 0. That's what we wanted. And negative 1 times 13 is negative 13. Plus 15 is 2. All right, you guys. Your ordered pair here is 2, negative 1. That's the final solution. If you'd like, you can rewrite this in system form. This tells you 1x plus 0y is 2. That is to say, x is equal to 2. The second equation says 0x plus 1y is negative 1. That is to say, y is negative 1. In other words, the solution is 2, negative 1. This system would be consistent because there's a solution. Don't lose sight what is happening graphically here, because you have a pair of linear equations and two variables. We're talking, graphically speaking, we're talking about two lines, and we have found the point of intersection of the two lines to be 2, negative 1. You would say that this system is consistent. Very good. This is the Gauss-Jordan Elimination method. Okay guys, the next example, solve this system using matrices. I'm going to first rewrite this using a matrix, right? So the first row of entries will be the coefficients of the first equation. The second row will be the coefficient of the second equation. Now, for this example, you guys, it's not super easy to get a 1 right here. Keep in mind, I could divide this whole row by 2, and I would get a 1 right here. But if I divide this row by 2, although I get my 1 here in this entry, I would get 3 halves and negative 5 halves, and I would have to deal with fractions for this entire process. And so I'm going to try to get around having fractions. So instead of going for this entry to be a 1 first, I'm going to focus on getting this entry here in the second row, first column, to be a 0 instead. And I can do that if I multiply the first row by negative 3 and then add it to the second row. Okay, I copy down row number 1 so that I do not accidentally change it. But it is row number 2 that we're changing, and this is how we're changing it. We're going to multiply row 1 by negative 3 and add it to row 2. So 2 times negative 3 is negative 6, and negative 6 plus 6 is 0. That's what we wanted. Next, 3 times negative 3 is negative 9. Negative 9 plus negative 5 is negative 14. And then negative 5 times negative 3 is positive 15. Positive 15 plus 13 is 28. All right. So we got this entry in the second row, first column, to be a 0. I can pretty simply get this entry here to get to become a 1 if I divide the second row by negative 14. Okay, it's row number 2 that we're changing, so let me copy down row 1. All right, good. Now, row number 2, I'm going to divide all of its entries by negative 14. 0 divided by negative 14 is 0. Negative 14 divided by negative 14 is 1, and that's what we were after. And then finally, 28 divided by negative 14 is negative 2. Cool. So I have my 0 in the second row, first column, and the 1 in the second row, second column. My second row is perfect, you guys. Hey, by the way, this tells you right here that y, remember this is 1y, y is equal to negative 2. So we already know what y is. All right, I need to get my first row in order here. So what I'm going to do is I'm going to focus my attention on this 3. I need this entry to be a 0. I can do that. I can get it to be a 0 if I multiply the second row by negative 3 and add it to row number 1. All right, what I'm not changing is row number 2. So let me fix that in here. Okay, very good. All right, here we go. We are going to multiply 0 by negative 3, which is 0, plus 2, which is still 2. All right? And then 1 times negative 3 is negative 3, and plus 3 is 0. That's what you and I were trying to get. Good job. Negative 2 times negative 3 is positive 6. Positive 6 plus negative 5 is positive 1. All right, so the only thing that's missing from reduced row echelon form is this entry here needs to be a 1. I can do that by dividing everything by 2, or dividing all of row 1, that is to say, by 2. Okay, so 2 divided by 2 is 1, and that's what we wanted. 0 divided by 2 is 0, and 1 divided by 2 is 1/2. Finally, I have a fraction, but it's at the very end, and I'm done already. Okay, so what I want to emphasize in this problem, folks, is that when you go for reduced row echelon form, you can focus your attention on getting whichever entry you want. In other words, you don't have to get this leading one right here first all the time. Sometimes that leads to fractions. So then like in this example, the first thing I did was I'm going to get this 0 right here in the second row, first column entry. Sometimes I'll get this one here first. It all depends on how the matrix looks, and I'm just trying to do things in the most simple way, and I'm trying to avoid fractions. Okay, so you can see I can rewrite this in a matrix form if you like. The first row says that x is 1/2 and y is -2. So then the ordered pair at which these two lines cross is 1/2 comma -2. So you would say this system is consistent because there's a solution. Okay, everybody, here is a brand new system. Obviously, this is a system in 3 equations, so this is going to be more work, but it's the same kind of process. We want to solve using matrices. We want to get this matrix to be in reduced row echelon form. So here's my augmented matrix, right? Or the matrix that just represents my system. I want this in reduced row echelon form. I want a 1 in this first row, first column entry. I can easily get a 1 right here. Well, you know what I could do is I can divide this whole first row by 5 to get a 1 here, but that would introduce fractions immediately. Instead, why don't we just swap these 2 rows? Swap row 1 and row 2. Okay, you can see that I wrote on the side here, row 1. This is an arrow going in both directions, and row 2 are being swapped. Row 1 and row 2 swap. Row 3 stays the same at this time. So here we go. We got a 1 in this first row, first column entry. What we want is a 0 here where the 5 is, and also a 0 here. Okay, remember that you only want, for reduced row echelon form, you only want 1s along the main diagonal. So allow me to highlight this for you. This is going to be your main diagonal right there. And that's where you want 1s. You want 1s along your main diagonal, and you want 0s everywhere else. Well, you want a 0 here, 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 and here. This last column here will be your solution. Those can be any real number. All right, so where the 5 and the 2 is, that's where you want 0s. And I can get a 0 where the 5 is if I multiply row 1 by -5 and add it to row 2, then this will be a 0. Simultaneously, I can get a 0 where the 2 is if I multiply row 1 by -2 and add it to row number 3. Okay, so I'm gonna get a 0 in both of these entries at the same time. Okay, and I'm gonna do that by adding a multiple of row 1 to row 2, and then adding a multiple of row 1 to row 3 as well. All right, here we have it. Everything that I'm going to do there in blue is written for you. That's my way of kind of like showing my work. Make sure you're using that subscript notation every time you're doing this work, okay? All right, guys, the one row that I'm not changing is row number 1. There. Now, let's go ahead and change row number 2. And I'm going to multiply all of row 1. It's written right here. I'm going to multiply all of row 1 by -5 and add it to row 2. So 1 times -5 is -5, plus 5 is 0. 2 times -5 is -10. -10 plus 9 is -1. -2 times -5 is +10, plus 1 is 11. -3 times -5 is +15, plus 8 is 23. Okay, now let us change row 3. We're multiplying all of row 1 by -2 and adding it to row 3. 1 times -2 is -2. -2 plus 2 is 0. And that's what we're after. We've got to do it to the whole row now. 2 times -2 is -4. -4 plus 7 is 3. A lot of arithmetic, right? -2 times -2 is +4. +4 plus 6 is 10. And then -3 times -2 is +6. 6 plus 11 is 17. There we have it. We changed 2 rows at the same time. I know that's probably feels a little dangerous, so be very careful if you're going to do that. Now remember I said that we wanted 1s along the main diagonal? You have a 1 right here. Well, it's a negative 1. You can get it to be a positive 1 if you just multiply this by negative 1. So let's do that. Let's multiply row 2 by negative 1. All right, I multiplied all of row 2 by negative 1, and here's my brand new row 2. All right, that's the only row that changed. Cool. Now I have 1 right here, 1 here, and eventually I need to get this 10 to be a 1 as well. I would like us at this time to shift our attention to this 2 and this 3, the entries that are above and below, above and beneath this leading 1 right here. I need the 2 and I need the 3 to be zeros. I can get the 2 to be a 0 if I multiply row 2 by negative 2 and add it to row 1. I can get the 3 to be a 0 if I multiply row 2 by negative 3 and add it to row 3. So I'm going to change row 1 and row 3 at the same time. I'm going to leave row 2 unchanged at the moment. All right, so here it is. I'm not changing row 2, so I copy that down. I'm going to multiply row number 2 by negative 2, add it to row 1, and that'll be my brand new row 1. 0 times negative 2 is 0, plus 1 is 1. 1 times negative 2 is negative 2, plus 2 is 0. Negative 11 times negative 2 is positive 22. Positive 22 plus negative 2 is 20. Telling you this whole process is just arithmetic, critical thinking and arithmetic. Negative 23 times negative 2 is 46. 46 plus negative 3 is 43. Okay, there's my row 1. Now my row 3 is going to change. I'm going to multiply row 2 this time by negative 3 and then add it to row 3, and that'll be my new row 3. 0 times negative 3 is 0, plus 0 is 0, so that 0 doesn't change, thank God, because we worked hard for that. 1 times negative 3 is negative 3, plus 3 is 0. Negative 11 times negative 3 is positive 33, plus 10 is 43. Negative 23 times negative 3 is positive 69. Positive 69 plus 17 is 86. Like that. Now what I notice is that I need this 43 to be a 1. I can easily attain that if I divide row 3 by 43. Okay, I did it. I took row 3 and divided by 43. 0 divided by 43 is 0. 0 divided by 43 is 0. 43 divided by 43 is 1. 86 divided by 43 is 2. All right, we are almost there, everybody. I need these 2 entries that are above that leading 1 right here. I need these 2 entries to be a 0. All right, now I can do that. If I multiply row 3 by positive 11 and add it to row 2, that'll make this entry to be 0. Simultaneously, if I multiply row 3 by negative 20 and add it to row 1, I'll get this entry to be a 0. So let's do both of those. All right, everybody, I wrote on the side what I'm about to do. I'm about to multiply row number 3 by negative 20 and add it to row 1 to change my row 1. Simultaneously, multiply row 3 by 11, add it to row 2, and that'll be my new row 2. Row number 3 is not changing. By the way, guys, this first column is for x, right? So this is 0x plus 0y plus 1z is equal to 2. So we already know our z value. We know that coordinate. Z is 2. So all we need are the other 2 coordinates. All right, so let's do this work now. So let's do it. Row 3 multiplied by negative 20. All right, 0 times negative 20 is 0. 0 plus 1 is 1. 0 times negative 20 is 0. 0 plus 0 is 0. But here we go. 1 times negative 20 is negative 20. A negative 20 plus 20 is 0. All right, so let's add those entries, what I just finished saying. So 1, 0, and then this becomes a 0, right? Now, 2 times negative 20 is negative 40. Negative 40 plus 43 is 3. Look at that. We just found our x value, guys. X is 3, right? 1x is equal to 3. All right. Now let's take row 3 and multiply by 11. So here we go. Row 3. So 0 times 11 is 0. And 0 plus 0 is 0. So that doesn't change. Also here, 0 times 11 is 0. 0 plus 1 is 1. All right, here we go. 1 times 11 is 11. 11 plus negative 11 is 0, and that's what you and I wanted. Finally, 2 times 11 is 22. 22 plus negative 23 is negative 1. All right, you guys, we're done. I want to emphasize something, though. This is your main diagonal. Okay, so you wanted a reduced row echelon form has you getting ones along your main diagonal, and you got zeros above and below, both above and below every leading one. So these are leading ones, right? So this one has zeros underneath it. This one has zeros above and beneath it. This leading one has zeros above it, right? And then your ordered triple. So here, let me be very clear here, as clear as I can. In a system form, this would be 1x plus 0y plus 0z is equal to 3. In other words, x is equal to 3. The second row says y is equal to negative 1, and the third row says z is equal to 2. So the point at which, and these systems of 3 equations and 3 variables define 3 different planes. And so you have these 3 planes, and they're all intersecting at a common point, which is this ordered triple here. That's an ordered triple at which the 3 planes intersect. You would say this system is consistent. That was fun, wasn't it? Okay, guys, to wrap this up, we're done here, but to wrap this up, I wanted to just emphasize something. What does it look like when you're solving a system using matrices and you get no solution? Well, let me just make something up really quickly. Imagine if you were solving a system, and let's just say this is your first row, and what if this happens? Look at that last row here. What would this mean as an equation? Well, that second row would say 0x plus 0y is equal to 4. In other words, 0 plus 0 is 4. In other words, 0 is equal to 4, which is a contradiction. If this happens to you, if at any point when you're using matrices, now keep this in mind, if at any point when using matrices, if one of the rows becomes all zeros except for the last number, then that means that you have a contradiction, and your final answer is no solution. No solution. Okay? I'm going to say that again. If at any point when you're solving using matrices, if one of your rows becomes nothing but zeros except for the constant, so you got 0, 0, and then just some constant number, that means you have a contradiction, and that means if you're talking about lines, then the lines never intersect. They must be parallel, and the system is inconsistent. If you have an equation in 3 variables and you're talking about planes, the planes never all intersect, right? So they must, the final answer must be no solution, okay? So remember that, and remember that if you have no solution, that means your system, the system, is inconsistent, all right? So keep that in mind. If this happens to you, where you have zeros and then a constant, don't automatically think you did something wrong. Maybe the answer is just no solution. Now, let me show you the other case, the other extreme case. If you get nothing but zeros, okay, if you get again, let me make something up really quickly. All right, look at this. If this happens to you, this is not no solution. I mean, look at this last equation. And it doesn't have to be the last equation or the last row. It could be any row. But look at this. This would mean 0x plus 0y is equal to 0. In other words, 0 plus 0 is equal to 0, just 0, 0, right? This is not a contradiction. This is an identity. So if this happens to you, at any point, if any of your rows becomes all zeros, then you can stop right now and just say your final answer is infinitely many solutions. What that means graphically speaking is that these two lines lie right on top of each other. They have infinitely many intersection points. If you're talking about planes, that means equations in three variables, that these two planes lie, or these three planes lie right on top of each other, having infinitely many points of intersection. Please don't say all real numbers. That's something different. So you say infinitely many solutions. In this case, the system would be consistent. Okay, the system would be consistent. All right, you guys, this wraps up our lesson, Chapter 6, Section 3 about matrices. I'll catch you in the next lesson. Good luck on this homework section. This was a lot of fun.